as mentioned, I'm going to introduce Voodoo, which is a scheme that combines memory tagging, authenticated encryption, and error correction through something called magic. So we want security in our systems. We've seen a lot of talks that were proposing new exploits, that were talking about vulnerabilities, but what we actually want, right, is our data to be secure, which means we need to have some way of actually securing our sensitive information. And in an ideal world, we would have just one button that we need to push that activates security completely free of charge. So once I push that button, everything is secure. Well, we did not find this button, except for maybe turning your computer off. So what we have instead is we have security building blocks, which means we have separate schemes or features that provide certain types of security in our computers. Consider, for example, these three. We have data encryption, in that case, the encryption of DRAM data, which means that an attacker cannot read the data that's stored in memory because it's encrypted. You can only read it with the correct key. If we were to use authenticated encryption, we could also tell who actually stored the data in memory, because only a party in possession of the correct authentication key can compute a MAC. Then we have tagged memory here in the lower left corner. Tagged memory is great for protecting against memory safety vulnerabilities, which are actually a huge problem because a lot of programs are written in C and C++ and are notoriously vulnerable to memory safety issues. And tagged memory aims to solve this by associating each allocation with some metadata that's also stored in memory. And when you access an allocation, you check the metadata if everything is fine. And in the lower right corner, we have DRAM error correction, which is like a bit low level, but it ensures that the data we read from DRAM is not subject to some random bit flips. Not only stuff like rowhammer, but also naturally occurring bit flips due to various sources. But it turns out each of these has some overheads. So data encryption, for example, if I'm using authenticated encryption, I'm having a memory overhead because I need to store the authentication tag. I'm also having a performance overhead because this encryption engine is usually placed on a critical path, meaning each time I'm reading from memory, I actually need to decrypt my data, which means the read will be slower. Tagged memory has a small memory overhead of 3% in the case of ARM's memory tagging extension, and also some small performance overhead. And DRAM error correction also has this 12.5% memory overhead in the case for SEC-DED ECC, for DDR4 memory. I won't go into too much detail there. So on their own, each of these schemes is okay-ish when it comes to overheads. The performance overheads are not that bad and the memory overheads are also manageable. But once you start to combine these security blocks in a single system, what you get is an accumulation of overheads. And you end up with a system where you pay for your whole DRAM and you can only use up less than 3/4 of that, which is kind of bad. So what's the solution for that? Well, we tried to create a combined primitive, and this is what we did in this work. We unify authenticated memory encryption, DRAM error correction, and memory tagging into one single thing that we call Voodoo. We find that it has a low overhead, just this 12.5% for the authentication tag, depending on the parameterization. And we also find that we have a reasonable performance overhead of 1.4%. This was in a simulated environment using Spec CPU 2017. Also, we find we can provide strong error correction. In this case, single block error correction, meaning errors have to be confined to a single ciphertext block. And we can also offer strong multi-block error detection. So if errors affect more than a single block, we can never correct them, but we can most likely detect them. So it turns out we are not starting from scratch. There's actually a mode that's called the magic mode that already combines authenticated encryption and error correction. And the way this works is depicted here. Easy, right? So it's not that straightforward. What's happening here is each message block is first encrypted and stored to DRAM and also multiplied by a power of a secret multiplier h. So consider this to be some polynomial. And these products are then summed up. In the end, we add some authenticated data D and we encrypt this whole thing and end up with the authentication tag T. So this additional data here is not encrypted, as you might see, but it's always authenticated, meaning that you can check the authenticity of this data block. Magic allows us to correct up to a threshold of bits in one of these message blocks. And the way it works is it allows us the correction in one of the ciphertext blocks. So this T here, this TTH, is a parameter that we can actually tweak. And when we read from DRAM, what we are doing to check if there was an error is we compute a syndrome. And in the case that a block, let's say in this case with index J, is faulty, the syndrome will equal the error that we see in this block multiplied by the power of H, so H to the power of J. And the actual magic of this mode is in the way how these H values are selected, these secret multipliers. Because they are selected in a way such that the Hamming weights of the errors, the error products, follow a certain constraint. And this constraint is formulated on the Hamming weight. I won't go into too much detail here. You can read that up in the magic paper or in the background section of my paper. Depends on how much time you want to spend on that. But yeah, by looking at the Hamming weight of this syndrome and then of the error location identifier, we can identify the faulted block. So how can we now include memory tagging in this scheme? Can we just go ahead and replace the authenticated data D with some memory tag MT? That would be really easy, right? Well, can we detect tag mismatches if we do that? Can we still correct errors? And can we read those tags? Because reading tags might be important depending on what tagged architecture we want to implement. So let's first have a look at how we can detect tag mismatches. This very complicated formula here tells us how the syndrome is computed when we read data back from DRAM. And if everything works fine, then all ciphertext blocks are the same after reading them back, which means those two sums cancel each other out, and what is left is this tag difference ET, which is the difference between the provided tag and the stored or encoded tag. Now, what values can we have in this error? Well, if we have no constraints on our tags whatsoever, any value. And this is a problem, because any value can mean a value that looks like a correctable error. So if we use this naive tag encoding where there's no constraints on the memory tags, what can happen is that our scheme sees that and says, oh yeah, that's a correctable error, I'm going to correct some ciphertext block, and what we end up with is not the data that we stored before. So that's an issue. Also, can we read tags? Well, we just do an access with an empty memory tag, it's set to 0, and this means that this tag difference that we see is just the tag that we have encoded before. Unless we see an error in one of the stored ciphertext blocks. Because in that case, what we will read is the encoded tag plus some error multiplied by the multiplier raised to the power of the index of the block. And if there are no constraints on the tag, again, we don't know that this is an invalid tag. So we just read back something from memory that's basically a tag combined with some weird stuff from a memory error, and we have no way of telling that. Well, the takeaway here is that naive encoding is just not suitable. We need to be a bit smarter to actually include tagging there. And we find that we can solve this issue by using certain tag encodings. Overall, we have 3 different tag encodings in the paper. I'm going to talk about 2 of them more in detail. So one key insight here is tags are usually pretty small for performance and storage reasons, so we don't need to allow tags that can fill up this whole 64 or 128-bit message block. So what we can do instead is we fix the upper bits of the tag to a certain pattern. That can be all zeros, all ones, your favorite number, your lotto numbers, it does not matter, as long as it's always the same pattern. Because what we get then when we compute a tag difference is an error where all the upper bits are always 0. And when we see such an error, we can say, okay, this is most likely a tag mismatch. In this case, we lose a bit of correction capability because it might happen that correctable errors map to an error that looks like a tag difference. In such a case, we treat this as uncorrectable because we can never correct tag differences. We have to abort error correction there and report it as a tag mismatch. So this is the check pattern encoding. We can even go a bit further, become even a bit more smart here and say, okay, we have this weird constraint on the syndromes, on these error vectors, on the factors there, that the Hamming weight has to be above some certain threshold. which means everything below this Hamming weight threshold is basically fair game for us. So when we encode our tags such that tag differences always stay below this Hamming weight threshold, we can uniquely distinguish between tag mismatches and correctable errors, which means in that case that we have an encoding that allows us fully deterministic memory tagging, so there's no aliasing going on between correctable errors and memory tagging, but we have a smaller tag space than other encodings because this is quite limiting. The Hamming weight that we can actually correct is not that high, so when we limit the tag space to be below that, then we don't get as many tag bits as with the other encodings. With these tag encodings, we then performed a case study. So we looked up some memory tagging schemes, and we looked up how many tag bits per cache line they need, and then we checked if we can accommodate this number of bits per cache line. And with f-bounded, so the bounded Hamming weight encoding, which is the strongest encoding that we have because it's deterministic in that aspect, we find that we can offer up to 15 tag bits in the case of 64-bit memory blocks, and we can even offer up to 36 tag bits if we have 128-bit sized memory blocks. We also did a simulation because we can't test it on real hardware, but we wanted to know how well we perform with respect to error correction if errors are confined to a single block. So we built a Monte-Carlo simulation, and we used results from different paper where they investigated how bit errors are distributed in modern DDR4 memory. So we used that to model our fault model, and then we let these faults loose on our scheme, and we checked how the number of correctable errors increases or decreases with an increase of the correctable bit parameter. And what we find here is, at first it seems like everything is fine. We increase until we hit a threshold value of 19, where we have an optimum where we can correct about 99% of all errors that we simulate. And after that, there's a steep drop. And the reason for that drop is because at this point, there's aliasing between the different error location indicators, so we cannot uniquely identify in which block an error occurred, and in that case, we have to treat it as uncorrectable. We also wanted to know, what happens if errors don't behave well, if they are distributed even over multiple blocks. And of course, our friend Monte-Carlo comes in again and saves the day. So we did a simulation, what happens when we distribute the errors randomly over all chips on the DRAM. And what we find here is we have almost 99% of multi-block identification. So when we see a multi-block error, it's very unlikely that we say, oh yeah, this is a correctable error. There's some optimum in that sense where aliasing is the worst. That's when we have a threshold of around 27. In that case, there are cases where multi-block errors look like correctable single-bit errors, but once we start increasing even more this threshold value, then we run again into the situation that it's not uniquely correctable, so the miscorrection rate declines again. So in conclusion, we come up with a way to combine authenticated encryption, DRAM error correction, and memory tagging into a single thing. We can provide up to 36 tag bits per cache line. We can offer strong single block error correction as well as strong multi-block error detection. Thank you.